Yes, just there. Good morning, one and all. So, am I audible? Please check. Now, please check the PPT is also visible. Yes, please give me information. Please confirm to me. Am I audible? And PPT is also visible.
Yes, sir.
Yeah, am I audible?
Yes, sir.
Yeah, thank you, ma'am. So, in my house, so I don't have the power. Okay, power has gone up to maybe 20 or 25 minutes. I'll take the class. If power has come, again I'll continue the meeting. Okay. Yes. Yeah, once again, good morning, one and all. Now, today we are going to discuss about the design of bevel gas and warm gas. That is module 3. Yeah, module 3, the design of bevel gas and warm gas. Now, what are bevel gas? As you know that the gas are the teeth which are formed on the cylindrical surface or cone surfaces. So, in the module 2, we discussed the design of the spur gear and helical gear. There, the teeth are formed on cylindrical surfaces. But here we consider the teeth are formed on where on a cone surfaces. Then those gears are called as a bevel gears. That's the one introduction. And second one, the teeth are formed on where on cone surfaces. Second one, the motion and power, the mechanical motion and mechanical power, it can transmit between two shafts when two shafts are intersecting. When two shafts are intersecting. Now let's see the camera here. Now consider two fingers. The four fingers show the axis here. Now if the two shafts are intersecting, right? It may be at any angle. So from 0 degree to 90 degree or more than 90 degree also. The two shafts are intersecting, then I want to transmit the power and motion from one shaft to another shaft. So when two shafts are intersecting, then you go for use what type of gear? The bevel gears. Again, just I'll show this. The two shafts are intersecting. Right? This is the introduction about bevel gear. Right? The bevel gears are the gears which are formed on the cone surfaces and it transmit the motion and power between two shafts whose axes are intersect. See that in the figure here, the way how the teeth are formed here, teeth are formed on the cone surfaces, right? And here those shafts are intersecting here, right angle to each other. In earlier in the spur gear and helical gear, when how the power is transmitted between two shafts are parallel, right? And two shafts are parallel, then you transmit the power by using the spur gear or helical gear. But when two shafts are intersecting, I want to transmit the power and motion between two intersecting shafts, then we go for use. The type of gear is bevel gears. Now, these are some of the examples for bevel gears. One is straight bevel gear. Straight bevel gear means the teeth which are formed here, the straight, right? That is called straight bevel gear. If the teeth are formed in a curve, right, then it is called as a spiral bevel gear. Yes, power has come. Yeah, now some of the applications where we can see that bevel gears are generally used in the automobile differential locking mechanism or in automobile rear axles. I want to transmit that motion power from the engine gearbox to the rear wheel of the axle. How do you transmit? With the help of a primary propeller shaft, secondary propeller shaft. Then we can see that from the secondary propeller shaft to the axle, there's the intersecting shaft. Those two are intersecting. Then engineers go for use the bevel gears to transmit the motional power from the engine gearbox to the rear wheel of the axle of the vehicle. And second one, if the simple one it is, you can see the handles again are opening and closing of some shop doors, some textile shop doors, or even in our college also you can see that for Nandini parlor you can see that opening and closing of that roof, that is a flexible the roof. You can what we go for here, rotating that, and that is what type of gears we use here, bevel gears. On some pressing machine also we use the bevel gear. These are some of the applications of bevel gears. Right? Bevel gears, the introduction. Bevel gear is a gears which are teeth are formed on the pole surfaces and it transmit the two shafts are intersecting. Yes, am I audible?
Yes, sir.
Okay. Yeah. Now the type of gear is called as a bevel gear. Right. Next. Now, what are the different types of bevel gears are there? Okay, there are different types of bevel gear based on how the teeth are formed on the cone surfaces. One, if the teeth are formed in this on the cone surface is a straight, then is called as a straight bevel gear. You can see here the teeth are formed in the follows a straight line. This is a straight bevel gear. If the teeth are formed in a curved shape, a cylindrical shape here. See that a curved shape. Then the type of gear is called as a spiral bevel gear. This is similar to spur gear and helical gears, right? But here the teeth are formed in curved, not an inclined here, curved shape. Then if the two gears are same in size and they connected in right angles to each other, means the what is the shaft axis here between right angle to each other and both the gears are the same in size, then that type of gear is called as, that type of bevel gear is called as a meter gear. And another one is a crown gear. Crown gear stands for here the gear which is not, the teeth are not formed on the core surface, it's formed on the cylindrical surfaces in the radial direction. And another one is the pinion is a the spiral gear it is. Again, then it is crawled over that. It's a crown over that. Another gear. There's a bevel gears. Crown bevel gears. These are two examples for crown bevel gears. And our last one, another one is iPod gear. iPod gear means, now see that here the shaft is not intersecting here, neither parallel nor intersecting shaft. See the one shaft axis is here, another shaft axis is here. Right? The two shafts are non-intersecting and non-parallel, neither parallel nor intersecting. Then if I want to use a bevel gear to transmit those, again we go for use. What type of gear we use? iPod gear. Again, see that in the front, in the top view of this here. Now this will be the shaft axis of the pinion. This is the shaft axis of pinion, and perpendicular to that, that is the gear axis. Now those two gears are neither parallel, non-intersecting here, right? Then again there is some offset distance between the shaft axis, that called as the iPod gears. And last one is zero gear. It is similar to the spiral gears, but having what is the mean spiral angle is 0. The spiral angle is 0. That is called as a zero bevel gear. The types of bevel gears are, one is straight bevel gear, spiral bevel gear, meter bevel gear or meter gear, iPod gear, crown gear, then zero gear. These are the different types of bevel gears. Usually we'll use, here we'll go for design only a straight bevel gear. We concentrate only a straight bevel gear. Now these are different types of bevel gears. Now when it comes to the shaft axis, the bevel gears transmit two shafts, they are intersecting. Right? How they are intersecting? If the shaft axis is that represents summation sign, if the shaft axis is less than 90 degree, then that type of gear is called as an acute bevel gear. Acute angle means less than 90 degree. If it is exactly the shaft axis is 90 degree, then it's called as a right angle bevel gear. And if both the pinion and gear having the same size, both pinion and gear are same size, then that type of and angle, shaft angle is 90 degree, then it's called as it is a meter gear. Then if the shaft angle is more than 90 degree, then the called as a obtuse angle, that is called obtuse bevel gear. So usually we follow what type of bevel gear here. If the problem the shaft angle is not mentioned, we'll go for assume the shaft angle. The angle between the two axes is exactly it is 90 degree. It's a right angle bevel gear. You can choose. You can assume it, right? Next, what are the terminologies? Yes, the slide is visible. It's clearly visible. The picture. Please confirm to me.
Yes, sir.
Yeah. Okay. So what are the terminology used? As you know that the shaft axis, the teeth are formed on the conical surfaces, the conical cone on the cone, so the teeth are formed called as a bevel gear. Then what is this called as a shaft axis, axis of the gear. Right, when you view from the front side, now this part we call as a the teeth which is formed at the ear, we call as a root of the gear tooth. This is a root, and where the two bevel gears contact each other, that contact point is called as a pitch point. The contact point is called as a pitch point, and an imaginary circle which is drawn for the pitch point is called as a pitch circle. Right? That see that you get a pitch diameter. Right? Another one is now this is the end. This is called as a face width of the bevel gear, and this is called as a crown at the top. And again in the bevel gear, you can see that the outer, in the core, the larger diameter, the portion we called as a heel, and in the inner diameter, means the cone, the diameter decreases here. That part we called as a toe. So these are the other two terminologies we use. The heel, which is point, we called as a crown. And the width of this, the tooth, we called as a face width. Now remember these three terminology. One is root, another one is pitch point, third one is the face. And then you go for a cone surfaces. A cone on the imaginary circle is drawn here, and imaginary cones which you formed here. There's a face which you consider is a face cone. On the pitch point we consider is a pitch cone. At the root we consider is a root cone. Then that is meet at that point is called as a, if you consider a cone, it will be called as a apex. Right? This is called as apex, and this is apex. This one is called as a base. Right? When you go for take the terminology for the cones. Right? Yeah. Now the circle, which are the imaginary circle which are drawn on the root, we call the root circle. At the pitch point, we call it as a pitch circle. At the face, we call it as a face the circle, but it will not called as a face circle. At the pitch point, some portion which is added above the pitch point, that is called as what? Addendum. The portion which is added above the pitch point is called as addendum. The portion which is deducted in the cone surfaces, that portion is called as a dedendum. Right? Then total working depth is the sum of the addendum and dedendum. Now when it comes to the left side here, this is a root here. The angle which is formed from the axis of the gear to the root cone, that angle is called as a root angle. And similarly for pitch circle, we call as a pitch angle. This is here very, very important is pitch angle, that is called as a delta. This is also called as a half pitch cone angle. Half pitch cone angle, delta. Similarly, if you go for face cone with respect to the axis of the gear, if you measure that angle is called as a face angle. And then if you take this, the difference between the pitch angle and the root angle, that angle is called as a dedendum angle. And the difference between the face angle and the pitch angle, that angle is called as a addendum angle. These are the terminologies which are used. Out of this, the very, very important terminology is pitch angle, that we represent as delta. This pitch angle is also called as off pitch angle. Off pitch angle. Right? These are the terminologies used for bevel gears. And one more very important here, the distance between the crown and the apex of the cone. That distance is called as a cone distance, or called as a slant distance, that we represent as R. This is also one of the important terminology. Cone distance or slant distance of the bevel gear, that we represent as R. The distance between the crown, or if we take this, at the apex here, sorry, at the base of the bevel gear, that is a crown to the apex. That distance is called as a cone distance or slant edge. You can see the slant edge of the bevel gear that we represent as R. These are the two important terms. One is pitch angle, another one is cone distance. Clear? On this you can see in the data handbook, that is a figure number 23.61. The definition dimensions of bevel gears. So whatever the theory portions, what we go for discuss, if you see the data handbook clearly by one page by page, almost all the sketches and explanation also you can get from the data handbook. That's why you can use properly, utilize the data handbook. You can see, right? Yeah, next you go for design of bevel gears. Again, as you know, the design of machine element procedure, same it is. It's a design of, it is an iterative process. This number of processes carried out here to assigning what? The specification of bevel gear. Again, what are the specification? It related four things. One is size, shape. First one is shape, size, then material and methods of manufacturing the component. Then last one is arrangement of component. There's also specification of bevel gear. Then withstand what? Loads. What are the different loads acting on the bevel gear? So one is the normal load, the static load. In the static load is a normal load acting on the commissioning of the teeth. The normal load resolved into three components. One is a tangential tooth load, that is the force which main causes to transfer the power from driver gear to the driven gear. Then radial or compressive load that acts along the radial direction. Right. Third one is the axial tooth load that is acting along the axis of the gear. These two forces will transmit to the bearings. Right. This is the force which main causes to transmit the power between the machine gears. Right. Now, design of bevel gear is nothing but it's an iterative process of assigning the specification of bevel gear to withstand loads or to do its function. What its function is? The function of gear is to transmit both motion and power from one shaft to the another shaft. Right. These are the specifications. As you know, the shape is that what type of tooth profile it is. It may be involute or cycloidal. Generally, we go for is involute. Under this, what is the pressure angle here? It may be 14.5 degree or 20 degree full depth involute or 20 degree stub involute. What will be the size of the bevel gear? It may be physical diameter, module, and other dimensions. The material and composition, again, it's made up of bevel gears are made up of these materials, and then methods of manufacturing means based on the method of manufacturing, we'll get the Brennan hardness number. Then arrangement of parts, how the parts are arranged. It may be acute angle or obtuse or right angle, or it may be as hypod to neither two shafts or neither column or intersecting, etc. Those are the arrangement of the parts. And these are the different loads acting on the gear. One is static load, it's a normal load that resolves into three components. One is tangential tooth load, radial or compressive tooth load, axial load. Second one is dynamic load, and third one is wear load. Next, if you go for design procedure, before going to take the steps involved or design of the bevel gear, what are the terminologies used? It is same terminologies, whatever we consider for design of spur gear and helical gear, same terminologies we use. Some of the additional terminologies, what are the additional terms which you can use here? Now here A is not the center distance between shaft is not there. The B is a phase width. C is a dynamic load factor or coefficient. C suffix a service factor. If the data is not given, assume medium shock, 8 to 10 hours duty per hours. KV or CV is a velocity factor that depends upon mean crystalline velocity. As you know, the mean crystalline velocity is equal to 5 dn by 60,000. And D stands for diameter, physical diameter. 1 stands for pinion and 2 stands for gear. E stands for Young's modulus. F stands for load. Again, FT, tangential tooth load, dynamic tooth load, wear load. I stands for speed ratio or velocity ratio. It's a ratio of the speed of driver to the speed of driven. Then K is the load stress factor. M is the module. N stands for the speed at which the pinion and gear is rotate. 1 stands for pinion, 2 stands for gear. Capital P stands for power, small p, it is not capital P, it is small p stands for circular pitch. As you know, circular pitch is pi into module, or module is nothing but d by z. And Q is the ratio factor, R is the physical radius of the gear, and one more additional terminology is capital R. What is the capital R stands for? It is a cone distance or slant height of cone. It is the distance between the apex of the cone to the crown of the gear, bevel gear. Bm is the mean piston velocity, small y is the Lewis tooth form factor, capital Y is pi into Lewis tooth form factor. Now Z is the number of teeth on the gear. 1 stands for pinion, 2 stands for gear. Again, here also, you can see the Z suffix V, virtual number of teeth. Here also, virtual number of teeth means it's imaginary number of teeth. When you take that number of teeth, that is equivalent to the spur gear. Now, how do you get this virtual number of teeth here? That is Z1 by cos delta we get. That you can see the data and look, equation number 23.4 and 23.426. And some other terminology symbols we use here. One is sigma suffix naught is all about static stress. Then alpha is the pressure angle. Now is another terminology is delta, half pitch cone angle. That is the angle between the axis of the gear to the pitch point or pitch point of the gear, bevel gear. That's called as a half pitch cone angle. Or the angle between the axis of the gear and the pitch cone, right? Pitch cone. That is a half pitch cone angle. Then how do you get this half pitch cone angle? Based on the shaft angle, you can use that from the equation where is from 23.407 to 23.407 to 23.412 for both pinion and gear. You can use this equation. Now, what is the shaft angle? The sum of the half pitch cone angle for pinion and the gear. That is the shaft angle. Again, as you know, the shaft angle is equal to 0, is the right angle equal to 90 degree, is the right angle. Bevel gear is less than 90 degree, acute bevel gear is greater than 90 degree, then it's called as a obtuse bevel gear. Right? Next, addendum angle that we represent as gamma suffix A. Gamma suffix is addendum angle. There's an angle between the face angle and the pitch angle. Similarly, detendum angle is the angle between pitch angle and the root angle. Now, it is the next one is cutting angle. It is the difference between the half pitch cone angle and the dedendum. Then face angle is the sum of pitch cone and addendum angle. Right? These are some of the additional terminologies which are used in bevel gears. Yeah, now we'll go for design procedure of bevel gear. Again, same procedure. 5 steps are there. First, identify weaker member. How do you identify weaker member? If both the gears are same, both the pinion and gears have same material, it's made up of same material, then you go for choose the pinion is the weaker member. If both pinion and gear are made up of different material, then you go for construct the table. Then you go for construct this table. What is the table contains? One is particulars, 1 stands for pinion, 2 stands for gear, then all over static stress, in Newton per mm square. Next, third column is Lewis tooth form factor. Then product of all over static stress and Lewis tooth form factor, that gives a load carrying capacity of the gear. If the load carrying capacity always we go for design is less, which is the load carrying capacity is less, that will be the weaker member. Means when you compare these two, the load carrying capacity of the pinion and gear member, now which one is smaller value? That will be the weaker member. Then how do you take the all over static stress? By referring here table 23.18. That is what we use for the spur gear. How do you take the spur gear materials for the spur gear? In which table you referred here? The table 23.18. All over static stress for the material for the pinion gear you can obtain from the table 23.18. Then next one, Lewis tooth form factor. How do you get the Lewis tooth form factor? Then based on the pressure angle, that is alpha, and tooth form is the full depth involved or stub, right? Based on pressure angle and tooth form, we'll go for determine the Lewis tooth form factor, which is equation varies from 23.115 to 23.117. Here in this, the Z we can take as not the actual number of teeth, is a virtual number of teeth, that is equal to the equation 23.431, I think. That is, we get Z1 by delta 1. Yeah, 23.425 and 23.426. So what is 23.425 and 426? You can get Z is equal to ZV1, that is Z1 by delta 1. Again, delta 1 is unknown here. Then how do we get delta 1? Again, we'll go for a further equation which varies from 23.407 to 23.412. We get delta 1 and delta 2. Right? Then substitute was Z is equal to ZV1, that is Z1 by delta 1, that we get Y1. And Z is equal to ZV2, that is Z2 by cos delta 2, that we get Y2. Then which will take the product, which will product is a smaller value, that will be the weaker member. Design should be based on that weaker member. Next, second step, design against a static load. Then the design against static load, first to consider a tangential tooth load due to power transmission. As you know that already, we use this equation 23.87b. In this, P is what? Power in watt. C suffix S, service factor. That is, assume the data is insufficient is there. Medium shock, 8 to 10 hours duty per day, that we can choose. CS is 1.5. Yes. Next, N is N and R are the speed and physical radius of the weaker member. Now here, what is R is equal to D by 2. D is what? Physical diameter is module into Z. Module into Z divided by 2. That is the physical radius of the weaker member. This already we use this equation. Next one, tangential tooth load from the Lewis tooth form equation. What is the equation we use here? 23.433A. 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 Now you can see that in the data handbook, the design for gears on the bending stress. Now see the tangential tooth load here is the first term we'll use here. Ft is equal to sigma naught into K into KV into B into capital Y M into RB minus R minus B by R. That is a 23.433A. So what is sigma naught? Sigma naught, as you know that all of the static stress for weaker member, right? Then K suffix V is a velocity factor that depends upon mean piston velocity. Once you consider mean piston velocity, based on the mean piston velocity, we'll go for use the KV formula, which varies from 23.464A to 23.465A. That's the equation numbers we use. Or if we see here, with the velocity, mean piston velocity is less than 7.5, we'll go for 23.464A. That is, velocity factor is equal to 3 by 3 plus Vm. Similarly, more than 20 meter per second, then we'll go for use this equation. This is a velocity factor. One is sigma naught, all over static stress. Kv is a velocity factor. What is a P? It's a face width of the gear. Face width of the gear. That face width of the gear usually we assumed what? 10 times of normal module, right? 10 times of normal module. But here also we use one more is R by 3. R is stands for what? The slant edge or a cone distance. Now in this, which one is smaller value? The 10 times of module or R by 3. Which one is smaller value? Whichever is smaller, then we consider that will be the face width. Again, how do you calculate R? R is the cone distance, that is equal to M by 2 square root of Z1 square plus Z2 square. It is 2. Make it correction. It is a 2. M by 2 square root of Z1 square plus Z2 square. That we can get in the data handbook 23.421. The cone distance of slant edge. Okay, 10 minutes left. time. Once session is ended, please rejoin the session. Next, what is capital Y? Capital Y is equal to 5 times a small y. Small y is the Levy's tooth form factor. Next, small m stands for module in millimeter. Now, when compare these two equations, back substitute, when compare these two equations, 23.87 and 23.433a. Now, we'll get the condition. When you compare those two, we'll get the condition to check the module to determine the module. Then once you fulfill the condition, you'll get the module. Then by referring the table 23.3, you'll get the standard module for the gear. Standard module for the gear. Better you go for construct the table. Right? Once you determine the module, then you go for check for stresses. Again, how do you check for stresses? Again, first you check the induced stress. Induced stress is equal to sigma naught into kV induced. This is a modified equation of RE. This is the equation of 23.433a. Then after this, allowable static stress, allowable stress, that is sigma naught into kV allowable. Then whatever the induced stress should be less than allowable stress, then design is safe. Similarly, effective force and bending force. Effective force is Ft by kV, and bending force is, again, it is a modified equation of 23.433a by omitting what? Omitting kV value. Then you get the bending load of the tooth. Then check the effective bending load should be greater than effective force, or effective force is less than bending force. Then design is satisfactory. This is the way to check for stresses. That will complete the step number 2. Step number 1, identify the weaker member. Step 2, design against static load. In the design against static load, tangential tooth load from power transmission, tangential tooth load from Levy's equation. Then compare those two, will get the module by trial and error method. Then after this, we go for check for the stresses. Both induced stress should be less than allowable stress. Then effective force should be less than bending force. Then third step, then go for determine the dimensions of the teeth of the bevel gear by considering the table 23.1. 23.1. Apart from this, so we also calculate other dimensions, but these dimensions will not use. Okay. So if they ask for the in detailed dimension means, then you go for calculate. In detailed design means, then you go for use these equations to calculate outside diameter of the gear, then inside diameter, addendum angle, dedendum angle, face angle, all those things you have to calculate. That completes what? Step number 3. Step number 4, design against dynamic load. It is similar to the design against dynamic load. Again, it is similar to the spur gear, but equation number changes here. Ft is equal to Ft plus 21 times of Vm, Ft plus B into C. Ft already we know the tangential tooth load. Vm also we know that. Face width also we know that. Only unknown is C. There is the equation number what here? 23.468. How do you calculate C? The dynamic load factor. As you know that dynamic load factor depends upon 3 parameters. One is material for the pinion and gear. Second one is pressure angle. Third one is error in action. Here error in action is unknown. By referring table 23.32, you will get dynamic load factor. The error in action is unknown. Then how do you calculate error in action? Again, 2 methods are there. One is if I know the class of gear cut is a precision or class 1, class 2 gear cut, then we go for refer that figure number 23.34a. Or if you don't know the class of gear cut, then you go for use the mean piston velocity. Then refer the figure number 23.3435a. 23.35a. Then you calculate error in action. Then by referring table 23.32, you can calculate dynamic load factor. After this, once you determine dynamic load, design against dynamic load, then you go for design against wear load. This is the last step, right? This is the last step. Yeah. Then according to Buckingham's equation, the wear load will be the, what is the wear load? Is it D1 BQK by delta cos delta 1. Now this is pitch angle will come here of one pitch angle. that should be greater than or equal to dynamic load. That is the equation number 23.4708. Right? Where D1 is the physical diameter for the pinion, B is the base width of the gear, then Q is the ratio factor, that is get 2 times of Z2V divided by ZV1V plus Z2V. That's equation number 23.16. Then K is the load stress factor. If I know the hardness for the material, then you can use this formula. Otherwise, go for calculate K value. That should be greater than or equal to some constant will get. Where delta 1 is the half cone pitch angle for the pinion. Then by referring 23.37b for a given K value is greater than or equal to for the given pressure angle, then you go for determine BHM for the pinion and gear material. Then once you can get the determinant, we check the wear load should be greater than or equal to dynamic load, then design is safe. So these are the 5 steps you should follow. Right? These are 5 steps you should follow. And then after this, what are the other loads which are acting on the gear? What are the other loads which are acting on the bevel gear? One is a radial load. The radial load is Ft into tan point of cos delta 1. You can directly refer the equation number 23.43483. Another one is axial load. That is 23.484. Now here we're neglecting the friction. Neglecting friction means coefficient of friction will not consider. Okay, we're neglecting this coefficient of friction. The frictional force will neglect here. If you consider frictional force, then we can just have Ft tan alpha plus rho. What is the rho? Is a friction angle. The friction angle is called as tan inverse of mu. Again, how do you get the mu value coefficient of friction? By referring the table 23.97 or refer the figure 23.88. These are the other forces. In the problem, they ask for determine the radial force and axial force which are acting on by the bevel gauge. So more axial and radial force also act in the bevel gauge that will transmit to the bearings. Okay. Next, these are the assumptions we should follow. What is the first assumption? If the shape of the tooth is not given, pressure angle is not given, then you go for assume 20-degree full depth involved. Then what type of service here? Medium shaft, 8 to 10 hours duty per day. The shaft axis is a right angle bevel gear. Consider the shaft angle is 90-degree. Similarly, if number of teeth on the gear is not given, then you go for assume minimum number of teeth on the pinion to avoid the interference to determine only weak member. For 20-degree full depth involved, here it is Z1 is equal to what? 15. How do you consider Z1 is equal to 15? By refer the table 23.84. To avoid the interference. Interference means undercutting action of the between the machine gears. To avoid that undercutting, to remove the material, for that you go for avoid this interference, avoid the undercutting operation. Undercutting. Then if the gear matrix is not given, then you go for assume pinion is made up of alloy steel or case hardened. Then you go for determine what will be the material for the gear by equating the condition. Right? Yes, next one is problem. Yes, please take this problem, copy this. We'll go for solve this problem. At the same time, I'll send the PDF file to your group. Those who want, you can check or you can refer that. Okay. It's less than 1 minute. Time is there. Once session is ended, please rejoin the session.